With the challenge. Hmm? But I won't join advance, isn't it? That we're having like yesterday. Okay, so a phase is a portion of a system that has uniform physical and chemical characteristics. Examples of a phase. Oh, that's why happy there's no test. Maybe we bring back the test. Ah, because I'm not getting answers. They're worrying me now. What are you doing to write the exam? I'm asking you basic questions. What? Hmm? What is the phase? Give me examples of a phase. So I said liquid phase. Which other phase do you of a component? Solid phase. Which other one? Hmm? I said gas phase. The other one? It's vapor gas. What is it? It's a mixture of what and what? Yes. Okay. What about a mixture of liquid and solid? Mixture of liquid and solid, what is it? Right? When you're melting butter, first it's hard, you put it on a pan, isn't it? Straight from the deep freeze. What do you observe? Hmm? Begins the size, isn't it? Liquid, well, eventually the main mass will be in a molten state to be very soft, isn't it? It's not liquid and it's not solid, it's in between. That's a molten state. Okay? All right, so for let's look at water. That's the simplest we can use. With water, what do we say about water? Pardon? Yes, yes, it's recording right now. Yeah, we're ready. Yeah, if they're available, let them join right now. I should just use the last link. Those who are available can join them with 2 cents. If they join now, at least if they have questions, interact. Okay, let's look at water. That's the simplest form we have. Huh? What can you say about water? With an increase in temperature, what happens? So as time moves, isn't it? When you get that ice, you put it in a pot and you put it on the stove, you switch on the stove. What do you observe? So it will move from zero, isn't it? The temperature gradually over time will be till where? So when it reaches the boiling point, what happens? Does it exceed 100? So it will just be boiling at the same temperature. Okay. All right. Something else again. Let me just copy it as it is from here. When we look at pressure and water, so for water, it looks like this. So this time we have temperature again, okay? Celsius. And then here we have pressure, okay, in atmosphere, 80. So we'll prepare something like that. And like this. Does this look familiar from chemistry? So we have liquid here. We have vapor. And we have solid here. Okay. Pressure here we have 0.01. Here we have somewhere around 0.01. Then somewhere here. Okay, so here temperature was 20. Here was 0. 20.6. So on 200. Okay, so what do we observe here? So let's say if we want to boil water, we pick this particular temperature, let's say 40 degrees here. So if water is at this temperature 40 degrees, depending on where you are, if the place where you are, the pressure is, for example, below 0.01, it's about 0.005 here. It means that that water will be in which phase? The vapor phase, isn't it? Okay, so let's say if the pressure goes a bit high. So where are we currently? What's our atmospheric pressure right now? Do you know the pressure? Where we are right now? Can we approximate? What about the temperature? Are we able to approximate? Room temperature. What's the room temperature value we take? Or 25 degrees. For calculations, usually we use 25 degrees for pressure, isn't it? So let's get that water somewhere around. Be somewhere around here, isn't it? What about pressure? It's around 0.1 atmospheres, right? Or is it 1 atmosphere? We have no idea. At 1 atmosphere. Okay. So it means that at that particular pressure, water will have a defined state. That's a uniqueness of water. Okay. So it basically means that water at a particular temperature here in Zambia may not be the same somewhere in a place where there is a lower or a higher pressure. Am I making sense there a bit? So it means that in some places, water will boil at 80 degrees, okay, depending on the pressure of that place. In some places, water will boil at 100, okay, depending on the pressure in that place. So pressure basically influences the phases in which that particular component will be held. Is it making sense? So we use this a lot in the industry, isn't it? When we're trying to keep certain elements under pressure. So nitrogen under pressure will have a different phase, isn't it? So under pressure, it may be gaseous. Okay, when you put it to normal pressure, it will be liquid. Depending on the pressure, you're not even playing with temperature, but you're playing with the pressure. The states or the phase is going to change. No? Not making sense? So pressure, what do we use to measure pressure?
Temperature and pressure.
It's that far back. We left you a long time ago. What's the difference between pressure and temperature? What is temperature? Is that condition? That's too general. Even for measuring temperature. A thermometer. Okay. How do I drive this home? What is pressure? When you compress air, isn't it, you're putting it under pressure, right? There'll even be a gauge there telling you at what pressure you're compressing that air inside that particular tank, isn't it? Or tube, whatever those. Yes, right? That's pressure. What is temperature? I'm assuming you know what temperature is. You know, isn't it? But you're looking at pressure. So now, depending on where we are above sea level, isn't it? Zambia generally is how many meters above sea level? We don't remember. Okay, we'll assume we remembered was 1 point, isn't it? That will determine the pressure, isn't it? Why is it that it's hotter in valleys? Usually the pressure is different, isn't it? It all has to do also with the height above sea level. Okay, that contributes to the pressure, the atmospheric pressure, the localized atmospheric pressure in that place. So that will vary. So pressure will determine those factors. When it's about to rain, there's a certain pressure drop that we experience. Those who are older, our grandmothers, and they would usually have problems in their knees. Usually they'll just feel their knees, some weakness, and they'll say, I think, yala look. I don't know if you've experienced that with your older relatives. It's the pressure drop, really, that causes that. Others will have increased blood pressure. Okay, it's in response to those factors, usually to pressure around, especially around the rainy season. And that's a whole topic, different. It's geography. I want us to come back now to where we are here. We're looking at phases. So I picked on water because it's one of those. So pressure plays a role. However, when we're looking at phase diagrams, we assume that pressure is the same throughout. Okay, and we do not consider it as a fact. In industry, when you're doing when you're extracting iron and other metals, okay, in order to produce alloys or whatever it is that we want to make from those metals, the assumption that we make is that the pressure will be the same. So what do we consider? Temperature, yes. So we consider temperature and we consider composition in the case of alloys. Okay, what we call weight percent. So that weight percent is what you have on your x-axis, on your phase diagrams there. You see it? It says weight percent, isn't it? So that's giving you the composition of the alloys, of the components of that alloy. So take, for instance, the first one there, what do you have? You have lead, isn't it? And what? And tin, which will give you what? So soldering material, isn't it? Soldering material has a temperature of around approximately 200 degrees Celsius, right? So it has a low melting point, melting temperature. That's why it is ideal for welding. Because when you're welding, when you're joining two metals together, you're basically picking. To join those, you need a metal that has a lower temperature, right? So meaning your welding tip will be 200 degrees. Now imagine if 200 degrees was also the melting temperature of your other components that you're trying to join together. Will that joining be successful? It means that your components will also melt, isn't it? So meaning your welding material or your soldering material has to be at a temperature lower than the melting temperature of those components that you're trying to put together. Does it make sense? Okay, so that's one of the pluses that we have for solder. That's why it's widely used in soldering, because you're getting two small components from your phone. For example, your whoever repairs your phones uses a lot of soldering material. Okay, so we pick this one. What else do you see? What's on the left side? Where is it written tin? Where is it written tin? By the way, tin, tin is this one, isn't it? Why is it written? Where is it written? Is it on the left side or the right side? On the same phase diagram.
On the right side.
On the right side, isn't it? Okay, so what does that mean? And then there's 100% on the right side, right? So it means that at that particular point, the composition for lead is what percentage? It's 100%, isn't it? So if the composition for lead is 100%, what's the composition for tin? What about the composition for lead? Huh? It will be what? It will be 0. So with composition, the maximum is what? So meaning if it's a binary component, isn't it? Binary where you have two alloys. It means one will be, if one is 40, what will be the other one? 60, isn't it? If this one is 35, what will be the other one?
65.
Huh?
65.
65, yes. So you've understood, isn't it? So it's two compositions, two components making up 100%, a whole alloy. Okay, so meaning if one is 50, the other one will be? If one is 60, the other one will be? So you have two extremes there. Where it's written lead, and if it's 100, meaning they are 100% lead. So if 100% lead, then what's the other percentage? The other one will be carrying 0, isn't it? We've gotten the logic there. So now how do we know the x-axis? How do you determine it's for which component here? If there are two components. Let me have a look at it. So in this case, it basically means that here, lead will be 0. Sorry, the components here, this is what gives you, this is the giveaway that you have. Okay, so it shows you here, composition, weight percent, tin. Okay? So here on the y-axis, what do you have? Temperature. Okay, so temperature can either be in degrees Celsius or in Fahrenheit. Okay, so for us, we use the degree Celsius. When in the exam, you find as degrees Celsius. Then the x-axis, it says composition in brackets, weight percent of tin, right? So it means that 10, 20, 40, 60, 80, 100 is tin. To make this make sense here, it even says tin is what? So meaning when tin is 0, lead is 100. When tin is 20, lead is what? 80, exactly. We get it now. Okay, all right, let's move forward. Okay, let's move forward. Okay, question 1. Cite the phases. Cite the phases that are present and the phase compositions for the following alloys. Have you written that they can log in if they're available? Have you invited those who are not yet? Cite the phases that are cite is what? CITE, eh? Not SIPHCI. Cite the phases that are present and the phase compositions for the following alloys. And the phase compositions for the following alloys. So A. 5 weight percent, tin, and 25 weight percent lead at what temperature? At 175 degrees Celsius. 75 weight percent tin and 25 weight percent lead at 175 degrees Celsius. Supposed to cite the phases that are present and the phase coefficient. So, what's the first thing you do? You find that point, right? Find that point on your phase diagrams. Have you located it? Using pencil. Please invest in pencils. And rulers. What phase is that located? See that you need your ruler and your pencil? Yes. Actually, it's 75, yeah? 75 T. see why you need to carry your rule and your pencil, okay? So you're going to give that point where on the question paper, that's where the phase diagram will be. However, in your answer sheet, what are you writing? What you're calculating, isn't it? You're giving me points, you're pulling it, okay? What is it? What's the problem? You can't imagine yourself. What? Don't worry, you'll land. I'm sure you must be somewhere, Kapiri. Kafulafuta. Even better.
Did you get the correct?
Pardon? Yes. What is it saying there at the bottom? So I say that we didn't go through phase diagrams. Huh? Because if we did, I think in the lecture I addressed most of these questions. So now you can imagine your friends in the class. Let me try and mimic that one. So you have temperature here. Because you know what I've done? I've not even looked at the phases, because I'm assuming that you looked at that by itself. What does alpha mean? Huh? Wow. It's not even difficult to understand. So I even skipped this. I've gone straight to calculations because I have to assume that. Huh? Simpler one. They're all like this. This one is the simplest. It gets worse than this. Okay, so now before you give up on life, let's look at the board one more time. Let's try and understand what we have. This is what we have, isn't it? We have L here. What does L mean? Liquid phase, isn't it? What about the alpha?
So the beginning of the liquid.
It's a certain solid component, right? So alpha plus liquid means what? A solid, an alpha solid plus a liquid. So it's a molten phase. Okay? Then here we have the alpha solid. What do we have here? A solid phase. Okay? So this is a solid phase composed of a solid that has both alpha and beta particles. Okay? Or beta solids. If I say particles, it will sound like radiation. This is not radiation. Then here we have beta plus liquid. Then here we have L. Then what do we have here? And then what's the element? Is it lead? Yes, we have lead here, and then here we have tin. Okay, so remember this is a solid. And this is also a solid. And that's a solid. Okay, so now what do we mean by a solid composed of two components? Do we understand that? An alloy, isn't it? So an alloy will be a solid. Give me an alloy, a solid. Let's say zinc. Zinc is made up of copper and tin. Okay, so you have copper in one solid, isn't it? You have copper and then you have tin, right? Two components. So now, how do we make alloys? From your mind, just imagine, just think, how do you think alloys are made? By combining. So in what form? So they're in liquid form, isn't it? So you cannot combine alloys in solid form, isn't it? You can't get copper here and then you bring tin here, two metals, and say, I'm trying to make an alloy. It's not possible, isn't it? So they combine best when they're in liquid form, right? So that the mixing is thorough and even and uniform, right? Then we can call that an alloy. So what happens during solidification? So meaning production happens at very high temperatures, isn't it? For you to get copper to melt, what's the melting point? Copper, about 1,300 somewhere there. Let's assume 1,300 Celsius melting point for copper. Okay, and then you have tin there. It's on very high, above 1,000, right? So meaning in industry, you're working with very high temperatures. So basically, you have remember how you watch those documentaries and pouring copper? It's looking red hot. At that point, that's going to make alloys. Are we together? So now you have let's just make things more domestic. You get a dish. So obviously, when the dish has to have a higher melting point than this, isn't it? Otherwise, to melt together with your. So you get something. Okay, a mold. Usually, we use molds in industry. You get a mold, and you have those components poured. So now, for an alloy, we need to know how much copper do I need? What's the composition of copper in here? And the composition of zinc? Am I putting 50-50, sir? You can take a walk just for a minute, then come back. Is it 50-50 or what? What do we think? So it depends, isn't it? So there's some factors that have to go in the composition. You just don't say, okay, I have charcoal, copper this time. You have standards, isn't it? And there are certain properties that you're trying to attract. So if the copper is lead to, or whatever element is lead to in that element, it means that whatever properties is coming, is bringing into that alloy, there won't be that much, isn't it? Let's talk about corrosion. Let's talk about steel. Steel is made out of iron, what else? And carbon, right? So to make it resistant to corrosion, we add what? Chromium. So now the composition of chromium also matters. So in the case of stainless steel, chromium should be greater than or equal to 11 weight percent. Okay, so what does that mean? When you're getting, and then here, this one should be around what? Let's say 2.4%. 2.4%. Okay, so 11 plus 2.4, what's the balance there? This is 2.4. Okay, so 13, so 100 minus 13.4 is what? To be what? 80 what? Can we please be accurate? 86.6. Have we understood now? So why do we use percentage? Because if we use amounts, you have different modes, isn't it? So percentage is an easier way for us to get the fractions. We're basically getting the fractions or the ratios of how the composition should be like. So if we're going to get chromium 11%, so meaning the minimum, if this is the minimum chromium that is accepted, then that should be the value, corresponding value for iron, 86.6%, isn't it? And then the carbon there, will pick it as 2.4%. Remember, the maximum for steel that we can use here is what? 6.7. Because with increasing, the more you increase carbon in steel, the more brittle that steel becomes. Do you want a metal that is brittle? Usually we look for ductility, isn't it? Strength, ductility, hardness. So that's why we try to reduce these components. And as much as it brings in strength, okay, it also increases brittleness of the steel. So we limit this, and also this one ultimately has to be limited. Okay, because it may interfere with some of the properties that we're looking for steel. If this is too much. Remember, this one is just bringing anti-corrosiveness. So this helps the steel in ensuring that it does not rust when we mix it in this alloy. We can do this. We also mix what? Vanadium is also added to ensure that your steel is highly corrosive. Highly resistant to corrosion. Making some sense of it? Okay, so now let's come back here to our phase diagram. So now, nature, who came up with this? This was experimentation. Look at all the phase diagrams in there. These were engineers that were experimenting, looking at different compositions of alloys at different temperatures. Then they realized there was a relationship between composition and temperature. Okay, hence those curves. So those curves are standard, whether we produced that alloy in Zambia or in the United States, we all use that same diagram. Okay, it helps us understand how the various compositions will affect temperature or how temperature will affect. In short, it helps understand the interaction between temperature and composition of alloys. Okay, so now we have different types. So there are different ones depending on the alloy. So we have the single components system. So single component is the water, right? Or the water that we have. There's only one component, which is H2O, right? What if to that H2O you got a cup and made yourself some zinc? How many components are in that system? How many? No, don't overcomplicate. So you have sucrose plus water, isn't it? Let's take water as one. We'll start now talking about hydrolysis and disassociation of. No. We're not going that far. So we just have these to make us what? Zigolo. Okay? How many? So this zigolo, can it be frozen?